in the last class we have seen that how we have got we can categorize the problems, break down the problems into sub problems by considering one non-homogeneity at a time. So in fact we have seen how the sub problems can be divided in case of a parabolic partial differential equation as an example that we are discussing in the last class, and we have found out that by in the process of breaking down we have identified three sources of non-homogeneity in the governing equations, and we broke down the problem into three sub problems considering one non-homogeneity at a time. That has resulted into one sub problem that was well posed. So and two sub problems, those were the ill posed problem. So all the sub problems containing the non-zero or non-homogeneous initial condition and the homogeneous boundary conditions are called the well posed problem, and the sub problems having the homogeneous initial condition and non-homogeneous, at least one non-homogeneous boundary condition, is known as the ill posed problem. Now in this class we will be looking into how the ill posed problem will be converted into an well posed problem, and then we can directly go ahead with the separation of variable type of solution. So let us consider one ill posed problem. Sub problems that we have considered last time. So del u3 del t is equal to del square u3 del x square, and at t is equal to 0 we had u3 equal to 0, at x is equal to 0 we had u3 equal to 0, and at x is equal to 1 we had u3 is equal to 3. So again this problem has to be divided into two sub problems. One is time dependent, another is the time independent solution. So therefore u3 will be divided into u3t will be divided into two sub problems. One is u3t transient, which will be function of both x and t, and u3 steady state, which will be function of x only. So we divide this problem into these sub problems into another two sub parts. One is the time independent part, which will be function of x only, another is the time dependent part, which will be function of x and t both. So in this case, so what we will be doing, we will substitute this solution into the governing equation. So this is the mother problem for this particular two sub problems u3t and u3s. So how we will be getting the governing equation of u3t and u3s? We will be substituting back this equation into the mother problem. So if you really do that, this becomes del t of u3t plus u3s plus del is equal to del square del x square, and u3 we substitute u3t plus u3s. Now let us look into this, what it is. So del t, so this becomes del u3t del t, because u3t is a function of x and t both, plus u3s, which is a sole function of x. It is time independent part, so it is a sole function of x. So time derivative will be 0. So this will be 0 is equal to del square u3t del x square. That term remains same because u3t is a function of x and t both, plus u3s is a sole function of x. It is not a function of time. So therefore this partial derivative will be a total derivative in this case. So it will be d square u3s dx square. Now next what we will be doing, will be collecting the similar terms and formulate the governing equation of u3t and u3s. So there is only u3s is coming. So therefore the governing equation of u3s is d square u3s dx square will be equal to 0, and we need to have two boundary conditions. And what is the governing equation of u3t? So governing equation of u3t is del u3t del t is equal to del square u3t del x square. So this is the governing equation of u3s, and this is the governing equation of u3t. Next what we will be doing, will be setting up the boundary conditions and initial conditions of U3S and U3T. So, first we will be looking into the boundary conditions of U3S. What we will be doing, the boundary conditions of U3S and U3T will be satisfying the original boundary condition of the mother problem. So, let us look into the original problem. In the original problem, at x is equal to 0, our U3 is equal to 0. So, what is U3? U3 is nothing but U3T plus U3S is equal to 0. That means, at x is equal to 0, both of these quantities will be equal to 0. So, that means, at x is equal to 0, I have U3S equal to 0, and at x is equal to 0, I have U3T is equal to 0. So, that sets the boundary condition at x is equal to 0. Then at x is equal to 1, in my original problem, U3 was 3, U3 was 3, that means U3T plus U3S is equal to 3. Now, what I will do, I will be judiciously selecting, I will be associating the non-homogeneous part with the time independent solution, and if I do that, then my U3T will be 0 at the boundary at x equal to 0, x equal to 1. So, what is my aim? Why we are doing this? Our aim is to get a non-homogeneous initial condition and homogeneous boundary conditions for a partial differential equation to make it well posed. In order to achieve that, I will be judiciously associating the non-homogeneous part of the boundary condition to the time varying part only, making or forcing the boundary condition of the transient part or the partial differential equation part to be homogeneous. So, if I do that, then I can write at x is equal to 0, my U3S equal to 3, and at x is equal to 0, my U3T is equal to 0. So, that makes that satisfies the boundary condition of the original problem as well. So, these two boundary conditions will be good enough to solve the space varying part. So, therefore, what is the space varying part? If you look into the solution of governing equation of the space varying part, d square U3S dx square is equal to 0. So, therefore, what is the solution of this? du3s dx is a constant, and one more integration, u3s is equal to C1x plus C2. Okay. So, if you put these two boundary condition, that at x is equal to 0, u3s equal to 0, the first boundary condition x is equal to 0, u3s is equal to 0, that will give you C2 equal to 0. That means, u3s should be is equal to C1x. Now, we apply the second boundary condition at x is equal to 1. So, this is at x equal to 1, this is also at x equal to 1, because this is at x equal to 1. So, there is a mistake there. So, u3s is equal to C1x. So, at x is equal to 1, u3s is equal to 3. So, if you put that, then it becomes 3 is equal to C1, and therefore, u3s is nothing but 3x. This is the solution of U3s. So, U3s is equal to 3x. So, we got the complete solution of the time of the space varying part or the time independent part. Now, with this we will be formulating the governing equation of the initial condition of the time varying part or U3t. So, what is U3t? In the original problem, at t is equal to 0, U3 was equal to 0. So, therefore, U3 is nothing but U3s, which will be a sole function of x, plus U3t, which will be a function of both x and t, must be equal to 0. So, we write U3t should be is equal to minus U3s, that is x. And what is U3s x? That is the steady state solution, and we know the steady state solution. What is the steady state solution? We just found out that U3s is equal to nothing but 3x. So, U3t will be nothing but minus 3x. So, that makes my boundary condition, the initial condition, to be non-homogeneous, and the problem is now oil post problem. Now, we define the problem, we write down the problem completely. Del square, del u3 t del t is equal to del square u3 t del x square. At t is equal to 0, my u3 t is equal to minus 3x. At x is equal to 0, u3 t is equal to 0, and at x is equal to 1, u3 t is equal to 0. So, this makes the problem completely oil post with a non-homogeneous or non-zero initial condition and homogeneous boundary conditions. So, that is how an ill post problem can be converted into an oil post problem by further subdividing it into two sub problem. One is the time dependent part, another is the time independent part. So, once we do that, we can use the principle of linear superposition. So, u3 will be now the solution, u3 will be a solution of u3s, which will be a function of x, plus u3t, which will be a function of x and t, both by solving this. We have already solved this part. This is nothing but 3x in our example, and u3t is the complete solution of this by using separation of variable that we will be looking into later on. But before going down to the separation of variable, we have to define some special functions. We have to define the eigenvalue problem of Sturm Liouville problem, and then we will be looking into the several properties and theorems to satisfy this Sturm Liouville problem, or standard eigenvalue problem will be satisfying. Then we will be going into the separation or solution by separation of variable directly. So, what we will be doing next is that we will be looking into a special type of function, for example, d square u special ODE First, we will be looking into a ODE in the form of d square y dx square plus lambda y is equal to 0, subject to at x is equal to 0, y is equal to 0, and at x is equal to 1, y is equal to 0. So, both boundary conditions are homogeneous in this particular type of ordinary differential equation. So, what is the solution of this ordinary differential equation? The solution is y equal to 0 is a solution. Solution must be satisfying the governing equation as well as the boundary condition. So, if y is equal to 0, that will be satisfying the governing equation as well as the boundary condition, but this is not a solution. So, this is known as a trivial solution. So, y equal to 0 is known as a trivial solution. So, what is the next question? The next question is there any existence of non-trivial solution? So, if so, there may be certain values of lambda, the parameter that is a constant parameter that will be appearing in the governing equations. There may be some kind of lambda that will be existing for which the governing equation becomes satisfied, and that is called a non-trivial solution. So, let us look into the non-trivial solution. Non-trivial solution can be obtained for certain values of lambda, the constant. These values of lambda are known as the eigenvalues of the problem, and the corresponding solutions are known as the eigenfunctions. And whenever we will be talking about this type of problem, d square dx square plus lambda y, lambda is a constant and the boundary conditions are homogeneous. This type of problem is known as a standard eigenvalue problem. So, these lambdas are known as the eigenvalue, and the corresponding solution is known as the eigenfunction. Okay. And whenever we talk about an equation like this and the homogeneous boundary conditions, then this is known as a standard eigenvalue problem. So, this is a standard, A is a standard eigenvalue problem or a Sturm-Liouville problem. This is a special type of Sturm-Liouville problem. We will be looking into the generalized Sturm-Liouville problem probably in the next class itself. So, in a standard eigenvalue problem, the necessity is that the form of the equation will be like this and the boundary conditions have to be homogeneous. So, in a standard eigenvalue problem, you should have the boundary conditions homogeneous. So, you should have homogeneous boundary conditions. So, next what we will be doing, we will be looking into the solution of this type of equation and we will be identify the eigenvalues and eigenfunctions and see how these eigenvalues and eigenfunctions they change for different kinds of boundary conditions. Now, first type of problem we solve, let us say case 1. Case 1 will be d square y dx square plus lambda square y is equal to 0. Let us say lambda y, lambda is the constant, and at x is equal to 0 we have and x is equal to 1, both the boundaries we have y is equal to 0. This is a case of Dirichlet boundary condition. Now, the parameter lambda can be, we will have three options. Lambda can be 0, lambda can be positive, lambda can be negative. So, we will be looking all the cases one by one. So, sub case 1, lambda is equal to 0. So, let us look into the sub case 2 will be lambda is positive, lambda is equal to alpha square, and sub case 3 will be lambda is negative. So, lambda is minus alpha square. So, lambda 0 positive and this is negative. So, let us go by case for lambda is equal to 0. Let us see what happens to our solution. Our solution is d square y dx square is equal to 0 in that case. So, dy dx, so y is equal to c1 x plus c2. Okay. So, now let us put the boundary condition at x is equal to 0, y is equal to 0. So, first boundary condition x is equal to 0, y is equal to 0, this gives you c2 equal to 0. So, solution is y is equal to c1 x, at x is equal to 1, y is equal to 0 indicates c1 equal to 0. So, y is equal to 0. So, this gives you a trivial solution. So, trivial solution is not accepted. So, the sub case is not tenable, it is not agreeable. So, therefore, lambda cannot be equal to 0. So, sub case 1 is ruled out and lambda cannot be equal to 0. So, next let us look into the other one, lambda is negative. Let us say let us look into the sub case 3. Lambda is equal to minus alpha square. So, it becomes d square y dx square minus alpha square y is equal to 0. So, we know the solution will be in the form of m square minus alpha square equal to e to the power, solution will be in the form of e to the power mx, where m square minus alpha square is equal to 0. So, m is equal to plus minus alpha. So, the solution will be c1 exponential alpha x plus c2 exponential minus alpha x. Now, if you put the value boundary condition, let us evaluate c1 and c2 at x is equal to 0, y is equal to 0. So, 0 is equal to C 1 e to the power 0. So, that will be 1 plus here also it will be 1. So, C 1 is equal to minus C 2. In the next case, what we will do? We put the other boundary condition at x is equal to 1, y is equal to 0. So, 0 is equal to C 1 e to the power alpha plus C 2 e to the power minus alpha. So, C 1 is equal to minus C 2. So, therefore, C 2 will be common. So, e to the power minus alpha minus e to the power plus alpha. Now, e to the power, if we and alpha is a constant and it will be a positive, it will be a constant, and if you know what is the variation of e to the power alpha versus alpha. So, alpha will be for ever positive number. So, this will be e to the power alpha. What will be e to the power minus alpha? This will be e to the power alpha, and e to the power minus alpha will be like this. So, their difference will be a finite value and it will be never 0. That means, in this equation this part can never be equal to 0. So, what is the option be now left? The option is left, in order to satisfy this equation, C 2 must be equal to 0. Now, if C 2 is equal to 0, C 1 is minus C 2. So, that will also lead C 1 equal to 0. So, if C 1 C 2 both are equal to 0, then my solution is at 0. So, it is basically again we are landing up with a trivial solution. So, trivial solution is not sought for. So, therefore, lambda cannot be negative as well. So, what is the what is left now? The option now left is lambda has to be a positive value or lambda has to be equal to alpha square. So, let us look into the sub case 2. That d square y lambda is equal to alpha square, and governing equation now becomes d square y dx square plus alpha square y is equal to 0. So, as we know, all of us know about it, that this particular type of ordinary differential equation will be having the solution in terms of the sine and cosine functions. So, y will be is equal to C 1 sin alpha x plus C 2 cosine alpha x. Now, let us put down the boundary conditions and see and evaluate the constants C 1 and C 2, and let us look into the what happens to the boundary the solution of y. At x is equal to 0, my y is equal to 0. So, if you put that 0 is equal to C 1 sin 0 is 0. So, that will be gone. So, C 2 cos 0 is 1. So, C 2 equal to 0. So, my solution is y is equal to C 1 sin alpha x. Now, at x is equal to 1, put the other boundary at x equal to 1, my y is equal to 0. So, therefore, 0 is equal to C 1 sin alpha. Now, in this particular problem, if there are two options, C 1 is 0 or sin alpha is equal to 0. If C 1 equal to 0, then again we will be getting a trivial solution that we are not looking for. So, the other option is for not equal to C 1, if we in order to survive the solution, the C 1 has to be non-zero, therefore, sin alpha has to be equal to 0. So, from this sin alpha should be equal to 0 for C 1 not equal to 0. So, what is the solution of sin alpha equal to 0? Alpha is equal to n pi, where the index n should runs from 1, 2, 3 up to infinity. The case n is equal to 0 should be avoided, because that will be leading to the first sub case and we will be getting a trivial solution. So, therefore, we write alpha n is equal to n pi, a subscript n to the alpha, in order to find out in order to indicate that we are talking about the nth root. So, in this equation the root is n pi, and so these are the eigenvalues of the system. So, eigenvalues are n pi, and alpha n is known as the nth eigenvalue. So, nth eigenvalue. So, what is the nth eigenfunction? Y n so we put a subscript n in order to indicate this is the nth eigenfunction corresponding to nth eigenvalue. So, y n will be nothing but C 1 sin n pi x. So, this is the nth eigenfunction. So, we have seen the particular in this particular problem that if we have dirichlet boundary conditions on the both boundaries, then for alpha is equal to n pi, we will be having the eigenvalues, and for corresponding eigenfunctions will be sin n pi x. If we have this alpha n is equal to n pi, then only we will be having a non-trivial solution for this particular system. Next, what we will be doing, we will be formulating the problem by changing the boundary conditions into Neumann and into the Robin mixed, and see how the eigenvalues and eigenfunctions will evolve. So, I will stop in this class. In the next class, what I will be doing, I will be taking up this problem again by changing the boundary conditions into Neumann, and then I will be taking up another problem by changing the boundary condition into Robin mixed, and see how the eigenfunctions and eigenvalues will be taking up the shape, and one will be getting the various types of solutions for such an well posed standard eigenvalue problem. Thank you very much.